Continuing with Chapter 4 on probability, we are going to be looking at the addition rule and the multiplication rule. So our key concepts in this section is going to be the addition rule as a tool to find the probability of A or B, which is the probability that either A occurs or event B occurs, or they both occur, as the single outcome of a procedure. The word "or" in the addition rule is associated with the addition of probabilities. You will also be looking at the basic multiplication rule for finding the probability that A and B, which is the probability that event A occurs and event B occurs. The word "and" in the multiplication rule is associated with the multiplication of probabilities. A compound event is any event combining two or more simple events. So here we're looking at the addition rule. Notation for our addition rule is going to be the probability of A or B, which means the probability in a single trial that event A occurs or the probability that event B occurs or they both occur. The intuitive addition rule. So to find the probability of A or B, you're going to add the number of ways that event A can occur and the number of ways B can occur, but add in such a way that every outcome is only counted once. So the probability of A or B is equal to that sum, then divided by the total number of outcomes in the sample space. So our formal addition rule is the probability of A or B equals the probability of A plus the probability of B minus the probability of A and B, where the probability of A and B denotes the probability that A and B both occur at the same time as an outcome in a trial of a procedure. So disjoint or mutually exclusive events. Events A and B are disjoint or mutually exclusive if they cannot occur at the same time. That is, disjoint events do not overlap. For example, a single six-sided die is rolled. What is the probability of rolling a 2 or a 5? So if I'm looking at the probability of rolling a 2 or a 5, then I'm going to be looking at the probability of a 2 plus the probability of rolling a 5. Now, we cannot roll a 2 and a 5 at the same time. So, again, it's a single six-sided die. So, the probability of rolling a 2 would be 1 out of 6. The probability of rolling a 5 is 1 out of 6. And you're just going to add here and get 2 out of 6. Here's another example of disjoint events. So event A, randomly selecting someone for a clinical trial who is HIV positive. Event B, randomly selecting someone for a clinical trial who is HIV negative. You cannot select a person that is both HIV positive and HIV negative. Events that are not disjoint or non-mutually exclusive. Event A, randomly selecting someone taking a statistics course, randomly selecting someone who is a female. So we could select a person that can both be a stat student and a female. So they are not disjoint. Let's look at some examples here of finding probabilities. And you will need to keep in mind disjoint and not disjoint at this point. So you're rolling a six-sided fair die. What is the probability you roll a 5 or a 6? So we're looking at the probability, rolling a 5 or a 6. You're going to look at what is the probability of rolling a 5 and add the probability of rolling a 6. And because these are disjoint, we don't have to subtract anything. We can just find those probabilities. So we're going to say probability of 5 is 1 over 6, and a probability of rolling a 6 is 1 over 6. So we have 2 sixths. What is the probability you roll an even number or a number less than 5? So here we have the probability of an even number or less than 5. So what is the probability of rolling even plus the probability of rolling less than 5 minus the probability that you're rolling even and less than 5. Okay, so the probability of rolling even, again, we're looking at a 6-sided die. So we have an even number would be 2, 4, and 6. So you have 3 over 6. The probability of rolling less than 5 is 1, 2, 3, or 4. And then the probability of rolling that it's even and less than 5 is going to be a 2 or a 4. So we're going to subtract those two pieces. And now we're going to add and then subtract, so 3 plus 4. So we get 7 over 6 minus 2 over 6. And 7 minus 2 gives me 5/6. Now let's look at what is the probability you roll a number less than 2 or a number greater than 4. So the probability a number less than 2 or a number greater than 4. So we're going to have the probability that a number is less than 2 plus the probability a number is greater than 4. And these are disjoint because we cannot have a number that is both less than 2 and greater than 4, so you don't have to worry about that subtraction part. A number less than 2 would be 1, so 1 over 6. And the number is greater than 4 is 5 and 6, so that's 2 over 6. And the 1 plus 2 is 3 over 6. Another example, a spinner has 4 equal sectors colored yellow, blue, green, and red. What is the probability of landing on red or blue after spinning this sector? So we're going to say, what is the probability of red or blue? So the probability of red plus the probability of blue. Again, we can't be red and blue, so we do not have to subtract anything here. So we're just going to say 1/4 plus 1/4, and that gives me 2/4. A glass jar contains 2 red, 3 green, 4 blue, and 5 yellow marbles. If a single marble is chosen at random from the jar, what is the probability that it is yellow or green? So the probability, yellow or green, so you're going to look at what is the probability it's yellow plus the probability it's green. We can't have a marble that is yellow and green, so we do not have to subtract anything because, again, these are disjoint. So I'm going to do the probability of yellow. Well, we need to know how many total marbles we have. So we'll do that. So we're going to add up 2 plus 3 plus 4 plus 5. So our total number of marbles is 14. So that will be our denominator when we're finding this. So we have yellow, we have 5 over 14, and green 3 over 14. And then you're going to just add across. So 5 plus 3 is 8 over 14. Go ahead and try these examples. You can pause the video here, and when you come back, you will see the answers. Here are those answers to the examples, and of course, if you have questions as you're looking at them, message in the Teams channel under Unit 2, and I will be happy to go into more detail. Let's look at some other examples of probability. If one card is drawn from a standard deck of 52 playing cards, what is the probability? It is a face card and red. So the probability, it's a face card and red. So what we're looking at here is a red face card. That should be 6 out of 52. If one card is drawn from a standard deck of 52 playing cards, what is the probability? It is a diamond and red. So the probability, a diamond and red. So the diamonds are red, so 13 out of 52. So here's a summary of the key points of the addition rule. So to find the probability of A or B, you first associate the word or with addition. To find the value of the probability of A or B, you're going to add the number of ways A can occur and the number of ways B can occur, but make sure that you are not double counting. So that's where you do that subtraction. Now we are going to look at the multiplication rule. So our notation is going to be the probability of A and B equals the probability event A occurs in a first trial and event B occurs in a second trial. The probability of B given A represents the probability of event B occurring after it is assumed that event A has already occurred. The intuitive multiplication rule. To find the probability that event A occurs in one trial and event B occurs in another trial, multiply the probability of event A by the probability of event B. But be sure that the probability of event B is found by assuming that event A has already occurred. So what does that formal rule look like? So the probability of A and B equals the probability of A times the probability B given A. Okay, so that conditional probability of B given that A has occurred, or probability of B given A, you want to make sure that you understand that that symbol means the probability of B given A. So independence and the multiplication rule. Two events, A and B, are independent if the occurrence of one does not affect the probability of the occurrence of the other. Several events are independent if the occurrence of any does not affect the probabilities of the occurrence of the others. If A and B are not independent, they will be said to be dependent. Let's look at an example here of screening drugs and the basic multiplication rule. 50 test results from the subjects who use drugs are shown below. Positive results was 45, negative test results is 5 out of the total of 50 people. We are going to look at these three different problems. If 2 of these 50 subjects are randomly selected with replacement, find the probability the first selected person has a positive test result and the second person has a negative test result. We're going to repeat that and do the same problem without replacement. And if 2 of these 50 subjects are randomly selected without replacement, find the probability the first person had a positive test result and the second person had a positive test result. So first we're going to look at the part A. If 2 of these 50 subjects are randomly selected with replacement, okay, so we got to be very careful here. We are with replacement. Find the probability the first selected person had a positive test result and the second selected person had a negative test result. So what we're going to look here is what is the probability of positive and the probability of negative. So the probability you're selecting a positive person is 45 out of 50, and the probability of selecting negative is 5 out of 50. So the probability that the first is positive and the second is negative is going to be 45 out of 50 times 5 out of 50. And you can just type this into Excel as 45 over 50 asterisk 5 over 50, and you should get 0.0900. Now for part B, we're doing the same thing. We are looking for the first person has a positive test result and the second person has a negative test result, but this is without replacement. So we're going to see something change here. So I'm going to have the probability that the first is positive and the second is negative, but we're doing without replacement. So if my first is positive, I have 45 over 50. But now I've picked one person out of our sample, so I only have 49 left, and our negative is 5. So now it's 5 over 49. You'll do your multiplication in Excel, and you get 0.0918. For part C, if 2 of these 50 subjects are randomly selected without replacement, find the probability that the first person has a positive test result and the second person has a positive test result. Okay, so if the first person is positive and we're selecting them out of the 50, it's 45 over 50. And since we are not replacing, when you pick another positive, we've already pulled one, so that means I'm only left with 44 over 49. So notice in this case, because we're doing a positive and a positive, that both the numerator and the denominator are changing. So enter this into Excel, and you should get 0.8082. Let's look at sampling. In the world of statistics, sampling methods are critically important, and the following relationships hold. Sampling with replacement, selections are independent events, and sampling without replacement, selections are dependent events. If you think back to the previous example where part A and part B, we had one with replacement and the other one without, because you saw that change in the probability with the without replacement, that shows that the events were dependent. The principle of redundancy is used to increase the reliability of many systems. Our eyes have passive redundancy in the sense that if one of them fails, we continue to see. An important finding of modern biology is that genes in an organism can often work in place of each other. Engineers often design redundant components so that the whole system will not fail because of the failure of a single component. So here's an example of modern aircraft are now highly reliable, and one design feature contributing to that reliability is the use of redundancy, whereby critical components are duplicated so that if one fails, the other will work. For example, the Airbus 310 twin-engine airliner has 3 independent hydraulic systems. So if any one system fails, full flight control is maintained with another functioning system. For this example, we will assume that for a typical flight, the probability of a hydraulic system failure is 0.002. In part A, we will be looking at if the Airbus 310 were to have one hydraulic system, what is the probability that the aircraft's flight control would work for a flight? And part B, given that the Airbus 310 actually has 3 independent hydraulic systems, what is the probability that on a typical flight control can be maintained with a working hydraulic system? So here we're looking at part A. If the Airbus 310 were to have one hydraulic system, what is the probability that the aircraft's flight control would work for a flight? So remember that probability of the hydraulic system failure is 0.002, and we're looking at the probability the hydraulic system does not fail. So we can do the probability 1 minus the probability of fail. So 1 minus 0.002, and that gives me 0.998. Now let's look at the fact that it actually has 3 independent hydraulic systems. So what is the probability that on a typical flight control will be maintained with a working hydraulic system? So what we're looking at here is the probability that not all 3 fail. So I would say, well, what's the probability of 3 failing? Okay, so we're going to do the probability of fail times the probability of fail times the probability of fail. So 0.02 times 0.002 times 0.002, or 0.002 to the third. You can put this in Excel as 0.002 caret symbol 3, and you should get 0.000000008. And because we're looking at the probability that not all 3 fail, we can do 1 minus the probability that all 3 fail. And that gives you 0.999999992. We will see this interpretation on the next page. So what does this mean? With only one hydraulic system, we have a 0.002 probability of failure. But with 3 independent hydraulic systems, there's only a 0.000000008 probability that flight control cannot be maintained because of all 3 systems failing. So by using 3 hydraulic systems instead of only 1, the risk is dramatically decreased and safety is dramatically increased. Here you can see a summary of the addition rule and the multiplication rule. So remember, the addition rule is for the probability of A or B, and the word or suggests addition. And make sure that you remember that when adding the probability of A and B, that we must add in such a way that every outcome is counted only once. The multiplication rule is for the probability of A and B, and the word and for 2 trials suggests multiplication. And when you're multiplying the probability of A and the probability of B, we must be sure that the probability of event B takes into account the previous occurrence of event A. For practice in this section, you can work on your My Stat Lab, section 4.2 homework, and your lab manual pages, 34 to 40. Please let me know if you have any questions in the Teams channel Unit 2 questions.